All right. How about the screen? Is it visible?
Yes, sir.
All right. Okay. So what did we do last time? We were talking about. All right. So yeah, we talked about temperature and how do we measure temperature. We talked about a device called thermocouple, and then we moved on to the temperature scale, where we talked about the Kelvin measurement really, and absolute zero and the triple point of water. So before we proceed with the next topic, which is the specific heat capacity, and really under it comes under thermal properties of material. So it's a thermal property of a material. Um, is there any question before we move on to that from the last lecture?
No, sir.
All right. Okay, so the goal is to study thermal properties of materials. And okay, so we'll start our discussion with specific heat capacity. Uh, Suppose that you have a body, anything, right? And I supply some heat to this body. What would happen? Obviously, supplying heat to this body means you're giving it some energy, which would cause an increase in the temperature, right? So when I give, upon supplying heat to the body, it increases the temperature, right? Increases the temperature of the body. Now, how much of the temperature has to increase? What I mean by that is, suppose you're giving it some energy. How can you measure the amount of temperature that will rise? Of course, if I give it more energy, what am I doing? Suppose there are some molecules sitting. This object is obviously made up of atoms, right? And so there are atoms sitting in there. And if I have supplied them energy, what would happen? They'd start vibrating more and more, right? They'd start vibrating more and more. The more energy I give them, the more energy they'll gain, and they'll start jiggling around more often. And we have already established that that is linked to temperature, and so the temperature would increase. So this temperature, how much of this temperature is going to increase? It depends upon the energy that I'll supply to my system. What does it depend on other than energy? If it depends on energy, energy and mass are really the same thing. It also depends on mass, right? So actually, I'll write it like this, right? So it depends on energy. It depends on mass because the more stuff there is in this object, so that means the more atoms there are, the more atoms start vibrating, the more the temperature would increase, right? And of course, it also, if it depends on the stuff, then it also depends on what material is this object made up of, right? So for example, if it's a metal tend to conduct heat more, and so the molecules would get more energy compared to, for example, if it were an insulator, right? And so it depends on on the type of material, really, right? So is this thing clear? Why does it depend on energy, mass, and the material? This should actually be delta T, right? Because it's the raise in temperature or any change in temperature. So what I'm saying is, what I've said so far is, so if I heat a body, its temperature is going to rise, and the amount by which it rises, that depends on energy, mass, and the material of this object. The energy supplied, the mass of the object, and the material with which this object is made up of. So, is that clear for everyone? Is it clear? All right. So, I cannot hear. Okay. Yeah, Omar said yes. All right. So, I'll assume it's clear. And now we can write an equation for this as delta T is equal to delta E by M, right? And this equation tells you how would the temperature change as I change my energy, right? Of course, you'd expect the mass to remain constant. So this equation is written as the change in energy is equal to the mass of the object, which is a constant, times the change in temperature. Sorry, there will be another constant in this expression as well. So I should have really written it like this. Delta T is proportional to that thing. And this another constant, it comes because of the constant of proportionality, right? And this constant is, I'll write it like this, M, and this constant is C. C is given a name, and it's known as the specific heat capacity, right? The C is known as the specific heat capacity. All right, now what is specific heat capacity? Anyone has any idea? Can you guess from this equation what should specific heat capacity be? Okay, so I'll tell you. Well, specific heat capacity is, um, you can think of it as, how do I say this? It is really the energy, right? It's really the energy that is required, that you require. You need this amount of energy to raise the temperature of your material by 1 Kelvin, right? So it's a fixed number, it's a fixed energy, and let me write like over here. So it is the energy that you would need to raise the temperature, energy required to raise the temperature of of a body, right? So you can say of unit mass by 1 Kelvin, right? So of course, if you're talking in terms of kelvins, then you'd say 1 Kelvin. If you're talking in terms of degrees Celsius, then you'd say by 1 degree Celsius. So you would define the specific heat capacity according to the temperature scale that you're using. So that's important, right? So, so that's the equation for a specific heat capacity, really. It is again delta E is equal to MC delta T. So is the idea of specific heat capacity clear? All right. Okay. So let's see if it really is clear, right? Let's do an example, right? Or let's just say let's do a problem. Suppose that you have a metal, a block of metal, and so this is a block of some metal, and its mass is, suppose it's zero point 0.5 kilograms, right? This is a block of metal, its mass is 0.5 kilograms. Uh, Can you scroll up for 1 minute? Alright, sure. Let me know when you're done. I think you're taking notes, right? But I'll share these notes with you anyway. So yeah. Okay. All right. So we were considering a block of mass. It is a metal and its mass is zero point 0.5 kilograms. Now let's say that I heat this block. I'm going to supply some heat, which essentially means I'm giving it some energy, right? And suppose I heat it with a heater or any candle with an output power of 36 watts, right? And let's suppose that I'm heating this for around 3 minutes, right? So I supply this heat for T equals 3 minutes. And then I stop it, right? So what happens is, of course, you'd expect the temperature to rise, right? So let's say that the initial value of temperature was some 12, let's say, degrees Celsius, and final value of temperature, so you're heating it for 3 minutes, suppose it's 26 degrees Celsius. So all of this is known. How can I compute the specific heat capacity for this thing? What I mean by that is, how can I compute what energy would I require to raise the temperature of, this block or metal by 1 Kelvin, right? So you can see how by how or we have units in degrees Celsius. So let's just talk in terms of degrees Celsius. You can see that a specific amount of uh, temperature has been risen, right? So if I want to calculate this thing, this would be 26 minus 12, which would be TF minus TI, and that's 26 minus 12 is 14 degrees Celsius. So we can see that the temperature risen was 14 degrees Celsius. And we want to see how much energy do I need to give this block to raise it by 1 degree Celsius. So that's specific heat capacity. So of course, if you have all of these quantities and you just want to do the math is very simple. But I went into some details so you can understand what do I mean by computing specific heat capacity, right? So we know that we know from this expression that delta E is mc delta T. We can write this expression for C as well, obviously, delta E by m delta T. All right. So you have to be careful because you are given this power in watts, right? And you know that power is energy per unit time. Power times time, and then power is it's 36 watts, and time is 3 minutes. But I want to write it in seconds, so I'll just multiply it with 60. And all of this is very basic stuff, right? So that's your energy, and C would simply be delta E, this energy. So it would be 36 times 3 times 60 divided by M, it's 0.5 kilograms, and delta T is the change in temperature, which is 14 degrees Celsius, right? So that's 14 degrees Celsius. And then you just do the math and you get 3 times 60, 930 joules per kilograms and per degree Celsius, right? So degrees. Anyways, most of it was just doing the math, but is the idea clear? Is the idea of specific heat capacity clear for everyone? Hello. Yeah, it's clear. Okay, so that's specific heat capacity, and we can now relate this specific heat capacity to a model that we have been talking about since the beginning of this topic or chapter, which was the kinetic theory model of gases, right? So let's do that. Let's relate this to the kinetic theory of gases. Specific heat and kinetic theory. All right. So we have already understood this thing that the temperature of a gas is really going to give you the information about the kinetic energy, right? So if you know the temperature, then you can have all the information about the kinetic energy. And we know that link is by 3 by 2 K times T, right? So having temperature, you have kinetic energy of the molecules. Now we'll use this theory of kinetic energy and temperature and extend it to liquids and solids as well, right? Any metals or non-metals. So we know that when we raise the temperature of any system, then the kinetic energy is also going to increase, right? That's understood. So let me write this thing. If I raise the temperature, then the kinetic energy would increase. Now, I could go again and explain in detail how that is the case, but I rather like any one of you to unmute yourself and try to give me an explanation for this, as this is something that we have already discussed before as well, right? So if you understand specific heat, the concept of specific heat capacity and how it is related to temperature, it's very simple that it is the energy required to raise the temperature by 1 unit, right? Whether it's Kelvin or degree Celsius. Then connecting specific heat capacity to kinetic theory is just to connect the temperature of a system to the kinetic energy of the system, right? So is that clear? So if I think in terms of the molecules, for example, again, uh, I would rather like you guys to tell me how would this be, but it seems that no one is interested in talking today. So I think I'll just go about it myself. Okay, so if I raise the temperature, again, it's the same thing repeating again. If I raise the temperature, the molecules would start moving faster. And if the molecules, they start moving faster, then that just means that their kinetic energy has increased, right? So you might be saying that our goal was to relate specific heat capacity to this kinetic theory of gases, right? But remember, what is specific heat capacity? It is the energy. It is the energy that is required to raise the temperature. So if you concentrate on these words, that it is the energy required to raise the temperature, then it's just really a form of a kinetic energy, right? So that's why I'm relating temperature and kinetic energy, and we're talking again about the same thing that we did last time. Okay, so is this idea clear?
Yes, sir.
All right, okay. So now let's talk about another type of heat, and that's latent heat. Okay, so I'm going to start this topic of latent heat by an example. Um, you know, for example, you have a block of ice, and if this ice is going to sit somewhere, right? Suppose it's sitting in a room, and of course, the temperature would be the room temperature, which is 300 kelvins, right? Or 23, 24, something, 27 degrees Celsius. Now, the temperature is constant, right? The temperature of the room, you can assume that it's not going to change. But you would note that the ice would start melting, right? After some time that passes, the ice starts melting, right? So I'll just draw these lines like this, which shows that it's melting. And so the ice started melting at a constant temperature. The temperature need not to be increased for the ice to melt. So it's sitting in a room, and suppose it's 300 kelvins in the room, the ice would start melting. You don't have to increase the temperature. The ice would melt all the way with a constant temperature, right? Now, of course, we know that if it's sitting in the room, right, some energy is being constantly or continuously being supplied to this ice. And what is that energy? That's heat, right? We talked about this in the last lecture. That's heat, because we stressed on this fact that it is heat that flows from one body or object to another. So the heat is flowing from the environment to this block of ice, but the temperature is not being raised. Now that's something counterintuitive, right? You would expect that if you're giving it some energy, it should increase the temperature, but that's not happening. That's not happening because, any guesses?
Because work is being done
Any
to
guess why?
move the particles apart.
Exactly. So that's a more technical way of saying this thing, that the energy is being used to change the phase of the system, right? So yeah, exactly. So you're doing some work to separate the molecules further apart. So separating the molecules further apart just means going from a phase of solid to liquid, right? So yeah, that's correct. So it will keep taking this energy, and then this energy is being used to uh, separate these molecules or atoms of this ice further and further apart, which would start melting this ice. And when the ice melts, it changes its phase from solid to liquid, right? Now, this energy that changes the phase of the system is known as latent heat, right? It's sometimes also called latent heat of vaporization or latent heat of fusion, just because of the fact that it's the heat that is, you can relate it to changing the phase of the system, right? So latent heat is just it's something like you're doing work. Work is done to change the phase of system. This work is known as latent heat. So is the idea of latent heat clear for everyone?
Yes, sir.
If there is any question whatsoever, I hope that you're not hesitating. Feel free to ask me any question if you have any. Okay, so I think there is no questions. Now, well, this is latent heat, right? Suppose we again talk about, we want to keep things to a minimum, right? So we can define something that is known as specific latent heat. Specific latent heat. Okay, so because we have discussed specific heat capacity, does anyone have any idea what would be the specific latent heat?
It's for a specific substance.
Almost right, but I mean, every substance would have its own latent heat, right? So that's already understood. Um, for example, ice would have a specific. So do not take the word specific literally. Um, specific means, I mean, yeah, you're almost right, right? So it means that it would be the energy that would be required to change unit mass, some unit mass of solid to liquid, right? So that's the most basic version of this thing, some unit mass, right? So you can say something like it is the energy required to change unit mass of solid to liquid, right? Or any phase, right? Solid to liquid. And then you could also have to gas, right? But okay, so I'll write it right over here: solid to liquid or gas. And of course, what is that one thing that we are not changing? Anyone? It's the temperature, right? So without causing any change in temperature, right? Now, what just happened? 1 second. Okay, where did it go? Yeah. So you can have specific latent heat, and now we'll just use two words. We'll just add two different words to this specific latent heat to define two different things. Specific latent heat of fusion means you're changing from solid to liquid. And specific latent heat of vaporization would mean that you're changing from liquid to vapor. Does that make sense?
Yeah.
So the word fusion is all right. So it's from solid to liquid, and the word vaporization. I mean, the word is very clear. It's from liquid to gas state of matter, right? And of course, you have to remember that in latent heat, you never change the temperature. So temperature is always constant in latent heat. So we can write down an expression for this as L, right? Where L is the latent heat, which is equal to change in energy per unit, or yeah, per unit change in mass. Now, you can obviously observe that there is no temperature in this equation. And you would not even expect temperature to be a part of this equation because you're not really changing the temperature. The temperature is kept constant when the phase is being changed. That's from the definition of latent heat, right? So L is the specific latent heat. Delta E, this thing, it is the energy that I'm supplying to the system. And delta M is that amount of mass which is converted from one state of matter to another state of matter, right? Is that clear?
Yes.
Okay. So then you can again write down two similar, very extremely similar expressions to this thing where you just add a subscript of F, which means that this is the specific latent heat of fusion, and that is change in energy. Or you can, it's change in energy, but you say that this is the energy that I'm supplying to the system, right? Divided by the change in mass. Now this mass is which mass? What changes this? Mass being converted from solid to liquid, right? Because that's fusion. And similarly, you will have the specific latent heat of vaporization. The expressions are exactly the same, right? But you should have an understanding of what these delta M really are, right? So delta E is always the energy that I'm supplying to this system. And delta M would depend whether the system is changing its state from solid to liquid or liquid to gas. So is that understood? Okay, so I'll assume that it's clear. And now let's do a problem for latent heat as well. Suppose that you have a kettle, right? And you are heating water in kettle. Suppose you want to heat some mass of water, and suppose the mass of water is 400 grams of water, right? So imagine that you're heating water in the kettle. The kettle supplies a power of 1.5 kilowatts, right? Now we want to calculate or find out what mass of water would be left in the kettle if I leave the kettle on for 5 minutes, right? So if I leave the kettle on for 5 minutes, of course, it's a practical thing, right? You are all familiar with it. If you're heating water in a kettle and if you let it heat, you start to see some gas vapors coming out of it, right? And those gas vapors are some of the mass of water being converted into those vapors, right? Because of course, conservation of energy, right? You cannot have these vapors being created out of nothing. So some of the mass of water is converted into these gaseous vapor, and we want to compute what mass of water is now left in the kettle after I have uh, converted this liquid to gas, right? So the kettle is being turned on for 5 minutes, and then support, and then you can say that the kettle is turned off. So there's one thing that you would need to find this thing. You would need the specific latent heat of vaporization of water. So for example, in a question, you're given different specific latent heats of fusion, vaporization. How would you know which one should I pick? Can anyone tell me? Suppose that you're given specific latent heat of fusion as well, and suppose you're given specific latent heat of vaporization as well. These are constants. These would be given to you when you're doing a question similar to this. Um, Anyone can tell me. So suppose this would be some value and this would be some value. Which one would I pick for this specific question? Which specific latent heat am I concerned with? I'll repeat the question. The question was that you have water that you're boiling in a kettle, and this water boils and turns obviously from liquid to gas, right? So which specific latent heat should I pick to solve the problem?
Specific latent heat of vaporization.
Yeah, exactly. You pick specific latent heat of vaporization because that is the heat that would be required or the energy that is required to change from liquid to gas, right? So, the specific latent heat of vaporization of water is 2.26 megajoules per kilograms, right? Now, we want to find the mass that is left. So first of all, I'll find the mass that has been vaporized. And how do I do that? Very simple. We know that specific latent heat of vaporization is equal to the ratio of the energy supplied divided by the mass that is converted, right? The mass that is converted from liquid to gas. So of course, now it's very simple. I can write this expression for delta M, which would be delta E by LV. And the energy can be computed by, again, just multiplying power with time. So that's very basic, right? 1.5 kilowatts times 5 minutes, but we want it in seconds, so 5 times 60 seconds. Divided by the latent heat of vaporization, which is 2.26 megajoules per kilograms. And this would give you an answer, right? And this would give you around 200 uh, grams, yeah, 0.199 kilograms, right? And this would be, you can write it in grams as 199 grams. What is this 199 grams? What mass is this? Anyone? So if
Is
you've
the
been
mass that
following
was
along, this is,
vaporized?
yeah, yeah, exactly. So this is the mass that has been vaporized. But we were asked what mass is left in the kettle, what mass of water is left. So what would you do? You would simply subtract from the total mass the mass that has been vaporized. So 400 minus 199, and that would give you 201 grams. So this is the mass that was left inside your kettle when you started